Today we are going to talk about phosphorescence. This video is aimed for a second semester general chemistry class that has already talked about molecular orbital theory, or an organic chemistry class. For this video, I will assume that you know how to identify the four quantum numbers and generally what they mean, how energy and the wavelength of light relate, and also molecular orbital theory, specifically highest occupied molecular orbital and lowest occupied molecular orbital. At some point in your childhood, you've probably had something that glows in the dark. Maybe a glow-in-the-dark soccer ball or glow-in-the-dark stars. But the question is, why do these materials glow? And the answer is phosphorescence. Very generally, phosphorescence is the emission of light in a similar manner to fluorescence, but on a longer time scale. So to adequately explain this, I will walk you through the basics of light emission, explain the differences between fluorescence and phosphorescence, and then explain why phosphorescence lasts longer than fluorescence. Before we get into the details of phosphorescence, we need to know the basics of photoluminescence. Bohr explains why molecules give off light. He uses the hydrogen atom as an example for this. So atoms have discrete energy levels where electrons could be around the nucleus. In this example, it is n equals 1, n equals 2, and n equals 3. When the atom is hit with a photon with the right amount of energy, the electron will absorb the energy and jump to a new excited state. Then, the electron will relax and fall back down to the ground state, emitting electromagnetic radiation, or light. Now we are going to do an interactive exercise. So this is an empty Bohr model of an atom. So I want you to label the nucleus, the ground state, the excited state, excitation, relaxation, and electromagnetic radiation. And I want the transition of the electron between ground state and excited state to be n equals 1 to n equals 2. Pause the video and get to work. So by now you should have filled out this diagram. If you haven't, you are being dishonest and not learning the material to the best that you can, so go back and do it. Alright, so as you can see, here's the answers. In the middle we have the nucleus. Number 2, we have the ground state at n equals 1. 3, excited state, n equals 2. 4, excitation. 5, relaxation. And 5b, electromagnetic radiation emission, or as I've said, light. So one principle to know about photoluminescence is before excitation, an electron is occupying the highest occupied molecular orbital, or HOMO. And then when it is excited, it goes to the lowest unoccupied molecular orbital, or LUMO, which is of course now occupied. So generally what I mean by HOMO and LUMO is, if you remember from the earlier part of my video, an electron gets excited from the ground state to the excited state in photoluminescence. So the highest occupied molecular orbital is the highest orbital that electrons are in, basically. And that's where your electron is excited from. Then, upon excitation, it occupies the lowest unoccupied molecular orbital, which is the next highest orbital in energy compared to the HOMO. And so this is where your electron is going to relax from and fall back down to your ground state and emit light. You will be reminded of this concept in a later interactive exercise that has to do with what happens to electrons in phosphorescence. Okay, so in photoluminescence, when the electron is excited, it can take one of many paths to relax back down to the ground state. One of the paths toward relaxation is a loss in energy that causes emission of light, known as fluorescence. That is generally seen in a lot of materials, such as quantum dots, as I have shown here. This is a diagram of fluorescence. Generally what it's showing is excitation of the electron from ground to excited state, and then energy loss in the form of light emission, or fluorescence. Another path that the electron can take when relaxing back down to the ground state and emitting light is phosphorescence. If we take a couple steps back and look at fluorescence again, when fluorescence occurs, the electron is excited to a singlet state and relaxes back down to the ground state from a singlet state. In phosphorescence, we have what's called an intersystem crossing, where the excited electron converts from a singlet to a triplet state. From the diagram, if you look at the triplet state, the highest energy vibrational state of the triplet state is approximately equal to the lowest energy vibrational state of the singlet state. But in the triplet state, you have further vibrational relaxation, causing the electron to lose more energy. Thus, when it relaxes back down to the ground state, it emits light at a longer wavelength because the electron has lower energy. And this is what gives you the longer lasting light, as you see in glow-in-the-dark materials. So the question to answer now is, what is a singlet state and what is a triplet state? So as I've mentioned in intersystem crossing, the electron goes from a singlet to a triplet state. So this is technically a change in spin quantum numbers or a spin flip. This spin flip can occur during absorbance or after excitation. And what you should know is that electrons can have either a +1/2 or -1/2 spin. So in the singlet state, electrons are paired spin-wise, meaning one electron has a +1/2 spin, the other has a -1/2 spin. In this diagram, that's represented by the arrow that's pointing up in the ground state and the arrow that is pointing down in the excited state. What is important to remember is before excitation, n = 4 was the HOMO and n = 5 was the LUMO. So now we have a triplet state. In the triplet state, the electrons are unpaired spin-wise, meaning the two electrons have the same spin. So if you add up the spins, they either equal 1 or -1. And that's represented on this diagram by the two arrows that are both pointing up. And what's important to note is the triplet state is always lower in energy than the singlet state. We're going to do another interactive exercise. So on the first set of energy levels, I just want you to fill out n = 1 and n = 2 with two paired electrons. Then in the second one, I want you to draw a singlet state where the excited electron is in n = 3 and the ground state is in n = 2. Same thing for the triplet state, except draw a triplet state this time. I also want you to assign the HOMO and LUMO of the non-excited energy level diagram. Now pause the video and start drawing some arrows. You should have filled out your diagrams now. And once again, if you haven't, go back and do it because then you won't actually understand phosphorescence. Alright, so here's the answers, and on the diagram I have labeled the HOMO and the LUMO just for your reference. Alright, and as we can see in the singlet state, the electrons are paired spin-wise, and in the triplet state, they are unpaired. As I've mentioned, the triplet state is of lower energy than the singlet state. So you lose energy in the intersystem crossing from singlet to triplet state, and also because the electron has to wait until it returns to its original spin state to go back down to the ground state. And this is because you can't have two electrons with the same 4 quantum numbers, that's stated in the Pauli exclusion principle. Basically what I have mentioned is the electron loses energy from vibrational relaxation and intersystem crossing. So the last question is, how does the electron go from singlet to triplet state? By electron rules, this should not happen. You should not have two electrons with the same 4 quantum numbers. Spin and orbital interaction makes the spin flip more likely, and something called spin-orbit coupling is what allows this to occur. For intersystem crossing, you need a molecule with a heavy center or nucleus, such as a metal, or a molecule with lone pairs. The large nucleus or the lone pairs can couple to the electron and give it the correct quantum angular momentum to do the spin flip. The spin flip is also more likely when vibrational levels overlap, such as in large molecules or molecules with lone pairs. What I mean by vibrational levels overlap is if you look at this diagram that I showed you before, you see the triplet state has many energy levels, and so do all the other singlet states. All molecules have these vibrational levels, and in molecules such as metals or molecules with lone pairs where there are more electrons, there are more vibrational levels, allowing greater overlap between the vibrational levels, allowing intersystem crossing. One other interesting idea is that paramagnetic species increase the likelihood of intersystem crossing as well because the nature of the molecule and its magnetic properties can attract or repel the electron, giving the necessary angular momentum to flip. And of course, there's much more to spin-orbit coupling that I'm not going to go into right now because it is a very complex topic. But for now, this is all you need to know about phosphorescence, and thank you for watching.